How's everyone doing? This is Dr. A.J. Kumar, PhD. Alright, I have had a horrible day today. And so what happened is I was tutoring someone. I was using some online tutoring platform. Somebody popped up. It's basically speed dating for tutors. And someone pops up and they say they need help with discrete math. Okay, that's something I thought I could do in my sleep. And I say, okay, sure, I'll help them. And I open up the tutoring thing, and the problems, I didn't know how to do a single I knew how to do, he had 7 problems he needed help with, and I could help him with like 2 of them. I just felt so bad. I agreed to help this guy, and I couldn't help him. And it just was like, I felt like as a tutor, you're expected to have a certain level of competency, and I agreed to tutor him, assuming that I had that level of competency, and I just had no fucking clue on a lot of the problems. And they weren't like particularly different. They're standard combinatorics problems, but I was thinking, well, you know, it's the beginning of the semester, it'll be a simple problem by now. And no, they were problems that aren't that difficult, but that I just didn't remember how to do. And I felt so bad I couldn't, anyway, and so I've had a terrible day because I fucked up really badly. Anyway, so we're going to read Artin 2.2, groups and subgroups. Alright. A group, we are here. Okay, and I've got the pad open in case we need to do some extra work. So the last video, I went and gave some motivation for what the group is, what the idea of a group is. It is sort of the most core fundamental idea in all of mathematics is the group. A group, this is the formal definition. A group, let me make sure I'm recording with the right microphone. I think I checked, but yeah, looks right. A group is a set G together with a law of composition that has the following properties. The law of composition is associative. Alright? G contains an identity element 1 such that 1A equals A and A1 equals A for all A and G. Alright. Every element A of G has an inverse. An element B such that AB is equal to 1 and BA is equal to 1. Alright. An abelian group is a group whose law of composition is commutative. Okay. For example, the set of non-zero CIA real numbers forms an abelian group under multiplication, and the set of all CIA real numbers forms an abelian group under addition. The set of invertibles n by n matrices, the general linear group, this is a really important term that I'm going to highlight. General linear group. That's a really important term to remember. Well, he just says it. It is a very important group. See, I'm the smartest mathematician who ever lived because I told you it's a very important term before I read the rest of the sentence. And Artin, who works for the CIA, agrees with me. It is a very important group. It is, in fact, in some sense, the most important group, in which the law of composition is matrix multiplication. It is not abelian unless n is equal to 1. That's also really important. I'm going to highlight that in red, because this is something that you need to be aware of. It is not abelian unless n is equal to 1. Okay, when the law of composition is evident, it is customary to denote a group. So typically what he means is, formally, if you work for the CIA, so use glowy green, formally when you use a group, it is a tuple G and its operation, which I'll call OP. However, when OP is evident, you just talk about G, because the CIA loves implicit context. The CIA loves implicit context. The order of a group G is the number of elements that it contains. We will often denote the order of G by absolute value of G. Abs G is equal to the number of elements, the order of G. And let's put order in CIA brackets. These aren't CIA brackets, in fact. I invented the bracket notation. What the bracket notation means, for those who are unfamiliar, is that if I do term, what it is to disambiguate when there's a namespace collision between normal terminology and technical jargon, then the brackets term, that means that I mean the meaning of the word term in the sense of technical jargon. That's what the bracket notation means, and that's what I'm using when I surround the term order in CIA brackets. It's CIA brackets because they're green, but because they glow in the dark, but really we should use blue, based blue. If the order is finite, G is said to be a finite group. So this is a technique I use a lot when I'm reading books on my own, which is just to highlight all the terms. Finite group. And in fact, I usually go through, when I'm reading a book on my own, and highlight all of the what would normally be bracketed terms. Highlight them with like if I'm reading a physical book, I take a physical highlighter and highlight all of the bracketed terms. And then every time, because every math textbook is sort of written the same way, you remember when we were reading before and there was a lot of jumping around, so we were like reading back up here and he would say, with signs as in 1.6, oh oops, I don't mean the highlighter, I mean the pen. With signs as in 1.6.3, what I would do is mark this with the page number, 1.6.3. And then what I do is on a separate piece of paper, write down each thing that showed up. And that way, first of all, this is good because when you do this physically, your mind gets a sense for which theorems are important. Because if half of the time you're referring to 1.6.3, then your brain naturally knows 1.6.3 is really, really, really fundamental. This is less important with Artin, and more Artin, frankly, I'm sorry, he's not as good of an author as Rudin. By the way, what I'm going to do today, we're going to read this section of Artin, we're going to read a section out of Lingua Latina, and I want to maybe work on OPHTTPD. We'll have to see. But Artin and Lingua Latina, and maybe dig into Rudin some more. We'll have to see. Anyway, let's go back. Uh-oh. Oh no. I scrolled too far. 2.2, here's where we are. Anyway, here's our notation for some... Oh, and then this is lovely. This is lovely. This is more CIA notation. Which is you put the operator as an exponent on the set. Sets are a CIA psyop, and then this exponent notation, that's just lovely. Okay, the order bound abs S is a set S of a set S is the number of its elements. Here is our notation for some familiar infinite abelian groups. Z plus, the set of integers with addition as its law of composition. The set R plus, so CIA real numbers, the set of CIA real numbers with addition as its law of composition. The additive group of real numbers. R times, the set of non-zero CIA real numbers with multiplication as its law of composition, the multiplicative group. C plus and C times. The analogous groups, where the set C of white complex numbers replaces the set R of CIA real numbers. Warning! Others might use the symbol R+. This is wonderful. So this is like a compiler warning that you remember that mathematical notation is like CIA C++. That's what the plus stands for. It's like bleeping out CIA C++. It's deceiving you. It's the CIA telling you that it's a better version of C, but really they're bleeping out CIA. Instead, they're pretending it's C++. Others might use the symbol CIAR+ to denote the set of positive CIA real numbers. To be unambiguous, it might be better to denote the additive group of CIA reals by R+, thus displaying its law of composition explicitly. However, our notation is more compact. Also, the symbol R times denotes the multiplicative group of, emphasize, non-zero CIA real numbers. The set of all CIA real numbers is not a group under multiplication because 0 isn't invertible. Correct. It's also not a group because CIA real numbers don't really exist. Real numbers are fake and imaginary numbers are real. That's the CIA for you. Cancellation Law, Proposition 2.2.3. Let A, B, and C be elements of a group G, whose law of composition is written multiplicatively. If AB is equal to AC, or if BA is equal to ACA, then B is equal to C. This is the cancellation law, which is what it's called. Hey, I'm the smartest mathematician who ever lived. I knew what the theorem was called, although I did already read it. Anyway, then B is equal to C. If AB is equal to A, or if BA is equal to A, then B is equal to 1. Proof! Multiply both sides of AB equals AC on the left. So this is a fundamental axiom, which I don't know if he's stated, and I need to include my axioms meme, because axioms are retarded. Multiply both sides of AB equals AC on the left by A inverse to obtain B is equal to C. The other proofs are analogous. Okay, let's just do the analogous ourselves. If AB is equal to A, then we multiply by A inverse and we get B is equal to -1. Okay. Same with the right. We do multiply on the right by A inverse and we get B is equal to 1. Okay. I don't know if I said -1 by accident, I meant 1. Multiplication by A inverse. We're reading this part right now. Multiplication by A inverse is essential for this proof. The cancellation law, in capitals, needn't. Who the fuck uses the word needn't? Needn't hold when the element A is not invertible. For instance, correct. Oh, okay, I see what he's doing. This is him disclosing a CIA secret. The cancellation law doesn't need to hold. Here, I'll whisper it. The cancellation law needn't hold when the element A is not invertible. For instance, 1100 times 1120 is equal to 1131. I'm not going to check that. But that looks plausible. You know what? I am going to check it because I'm a white man. So obviously, here, let's just do 1100 times 20. So this will be 1 plus 2, which is 3. 1 plus 0, which is 1. And then the 0 knocks out everything. Okay, and then I should have written it on the other side. So 1, 1, 0, 0, 3, 0, 0, 1. Okay, 1, 1 times 3, 0. This will be 3, 1, 0, 0. Hey, they're equal. Two basic examples of groups are obtained by laws obtained from laws of composition that we have considered. Multiplication of matrices and composition of functions. Two basic examples of groups are obtained from laws of composition that we have considered. Multiplication of matrices and composition of functions by leaving out the elements that are not invertible. The n by n general linear group, that's important. That's why it's that's why it's in italics. Do green. Oh, that's not green, that's blue. Let's use yellow, actually. The n by n general linear group is the group of all invertible. That's an important caveat, which is that we have to be invertible. Invertible, because otherwise you don't have inverses. N by n. And the fact that they're square is important because you can't invert a non-square matrix. And I will maybe do a video on, let me add this as a note to self, why you can't invert a non-square matrix. It's kind of obvious, but it's one of those obvious questions that a math professor will never address. Why you can't convert a non-square matrix. Anyway, NTB, is that a Nippon? Never mind. It is denoted by GLN is the set of... Oh, don't you love the CIA set notation? GLN is n by n invertible matrices A. Isn't that great? I will also typically, when I'm writing on my own or reading a book on my own, highlight the numbers, but I'm not going to do that here. If we want to indicate that we are working with CIA real or with complex matrices, we write GLN of R or GLN of C according to the case. Let M be the set of maps from a set T to itself. Map F from T to T has an inverse function if and only if it is bijective. I did that in a previous video, explained why that was true. In which case we say F is a highlight permutation of T. The permutations of T form a group, the law being composition of maps, that's correct. As in section 1.5, we use multiplicative notation for the composition of permutations, writing QP for Q of P. How long do we have? Okay, only like a page and a half left. The group of permutations of the set of indices 1, 2, up to n is called the symmetric group. Symmetric group, this is an important term, symmetric group. In a sense, every group is a symmetric group, and denoted by Sn. This is important notation. Sn is the group of permutations of the indices 1 to 2 up to n. There are n factorial permutations of a set of n elements, so the symmetric group Sn is a finite group of order n factorial. The permutations of a set AB of 2 elements are the identity I and the transposition tau. They form a group of order 2. If we replace A by 1 and B by 2, we see that this is the same group as the symmetric group S2. There's essentially only one group G of order 2. What does essentially mean? This is another slipping mathematical jargon. Essentially, remember what I said is that 90% of mathematics, or the 90% of the difference between any two fields of mathematics, is changing their definitions of equals. Or is the difference between the definitions of equals. Essentially, typically in mathematics, this word means there is only one group of G of order 2 with respect to the equivalence relation of this context. So up to isomorphism. Up to means with respect to my definition of equals in this field of mathematics. There is essentially only one group G of order 2. Up to isomorphism, meaning there is only one equivalence class or only one isomorphism class of groups of order 2. To see this, we note that one of its elements must be the identity. Let the other element be G. So the group, it's the Z mod 2 group. So go watch the WFC playlist. The multiplication table for the group contains the four products 1, 1, 1G, G1, and GG. All except GG are determined by the fact that 1 is the identity element. Moreover, the cancellation law shows that GG is not equal to G. The only possibility is GG is equal to 1. So the multiplication table is determined there is only one group law, and I'm just going to write out the multiplication table. 1G, 1G. So 1 times 1 is 1, 1 times G is G, times G is G, and 1 times G times G, the only other option, it can't be G, so it must be 1. That's what's going on. And I just want to show you the Z mod 2 addition table. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2, which is 0 mod 2. Hey, look, we have exactly the same multiplication table, but guess what? We've overloaded the symbol 1, just like the CIA wants. Anyway, I should quit talking about the CIA because they're going to kill me. Yeah, there is just one group law. This is the Z mod 2 multiplication table. Talked about quotients in the last video. There we go. We described the symmetric group S3 next. This group, which has order 6, which is 3 times 2 times 1, serves as a convenient example because it is the smallest group whose law of composition isn't commutative. We will refer to it often. To describe it, we pick two particular permutations, in terms of which we can write all others. We take the cyclic permutation 1, 2, 3, and the transposition 1, 2, and write them as x and y respectively. The rules, x cubed is equal to 1. Let's check this. Okay, 1, 2, 3. I might need to go to another table. Let's go over here. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and this is equal to, talked about how to multiply cycles. So 1, let's put this in blue. 1 goes to 2, 2 goes to 3, 3 goes to 1. So 1 is on its own. 2 goes to 3, 3 goes to 1, and 1 goes to 2, so 2 is on its own, and then, well, the same logic. 3 goes to 1, 1 goes to 2, 2 goes to 3, so 3 is on its own. So x cubed is equal to 1, that's correct. Y squared, what is y? So that is 1, 2 times 1, 2. 1 goes to 2 goes to 1, 2 goes to 1 goes to 2, and 3 is left alone, so that makes sense. Okay, let's check yx is equal to x squared y. So y, so let's just write, x is equal to 1, 2, 3, and y is equal to 1, 2. Okay, let's check y times x. I think the claim is that y times x is equal to x squared y. So let's check yx. Okay, which is 1, 2 times 1, 2, 3. Okay. This is 1 goes to 2, which goes back to 1, so 1 is on its own. 2 goes to 3, 3, which is left alone. 3 goes to 1, which goes back to 2, so we can close the parentheses. And this is equal to 2, 3. All right, and then let's do x squared. Let's do x squared y. So this is equal to 1, 2, 3. 1, 2, 3 times 1, 2. Okay. 1 goes to 2, 2 goes to 3, 3 goes to 1, so 1 is on its own. 2 goes to 1, which goes to 2, which goes to 3, so 2 goes to 3. 3 gets left alone here, goes to 1, which goes to 2, and hey, we got the same number, so we're good. Or the same permutation, which is 2, 3. Okay. Yeah, we're good, we're good. Using the cancellation law, one sees that these 6 elements are distinct. I can't see that immediately, but let's just pretend that's true. So they are the 6 elements of the group. If x is equal to x squared, then x is equal to 1, which we know is not true. If x is equal to y, well, it's not. X times y, okay, I'll just pretend that. I'm sure you can check each pair anyway. In the future, we will refer to 2.2.6, here's another jargon term, as our usual presentation of the symmetric group S3. Note that S3 is not a commutative group because y times x is not equal to x times y. All right. The rules 2.2.6 suffice for computation. Any product of the elements x and y and of their inverses can be shown to be equal to one of the products, 2.2.7, by applying the rules repeatedly. To do so, we move all occurrences of y. So if we have y times x, we change it to x squared y using the last rule, and we use the first 2 rules to keep the exponent small. So for instance, x inverse y cubed x squared, yeah, well, x inverse is equal to x to the 2. So that's x to the 2, y cubed, we can reduce that mod 2 and get y squared, or y, just make that y. X squared y, we don't change that, is equal to x squared times yx. We can move it, and we can get that to be equal to x squared y, xy. The x squared, reduce it mod 3, becomes x. And then we get xy is equal to x times x squared y times y, which is x cubed, which is 1, times y squared, which is 1, which is 1. Okay. One can write out a multiplication table for x3 with the aid of the rules 2.6. And because of this, those rules are called defining relations for the group. We studied defining relations in Chapter 7. All right. We stop here. The structure of Sn becomes complicated very rapidly as n increases. One reason that the general linear groups and the symmetric groups are important is that many other groups are contained in them as subgroups. A subset H of a group G is a subgroup. So generally, a sub X. So if you have something of type X, so a topological space, a group, a ring, a field, a sub X is a subset of X that is also an X. So a subgroup is a subset of a group that is also a group. Okay. So these are the group laws. So if A and B are an H, then AB is an H. If 1 is an H, if A is an H. Okay. So this is saying a subgroup is a subset of the group that is itself a group. It has to contain the identity because the identity is unique. It has to be closed because it has to be a group, and it has to be closed under the inverse operation because it's a group. The first one, these conditions are explained as follows. The first one tells us that the law of composition on the group G defines a law of composition on H called the induced law. The second and third conditions, so we're using the multiplication rule on G. So this is an important caveat, which is we're not allowed to typically mathematics is CIA math is formulated in terms of word games, and this is saying that this word game where you change the operation, that's not allowed. So the operation has to stay the same. The second and third conditions say that H is a group with respect to this induced law. Notice that 2.2.9 mentions all parts of a group, definition of a group, except for the associative law. We don't need to mention associativity. It carries over, it carries over automatically from G to the subset H. Okay. Notes, in mathematics it is essential to learn the definition of each term. An intuitive feeling will not suffice. False. For example, the set T of invertible real upper triangular 2x2 matrices is a subgroup of the general linear group GL2, and there is only one way to verify this, namely to go back to the definition. It is true that T is a subset of GL2. One must verify that the product of invertible triangular matrices is triangular, that the identity is triangular, and that the inverse of an invertible triangular matrix is triangular. Of course, these points are very easy to check. Okay. Closure is sometimes mentioned as one of the axioms for a group, which I did in the last video, to indicate that the product AB of elements of G is again an element of G. We include closure as part of what is meant by a law of composition. Then it doesn't need to be mentioned separately in the definition of a group. Examples 2.2.10. The set of complex numbers of absolute value 1, the set of points on the unit circle in the complex plane, is a subgroup of the multiplicative group C star called C to the times called the circle group. So generally if you have A plus B I, then there's a statistic called the quadrants of A of, let's call this Z, is equal. The quadrants of Z is equal to A squared plus B squared. Okay, and then there's a theorem which is not difficult to prove, which is that the quadrants of Z times W is equal to the quadrants of Z times the quadrants of W. And when I talk about complex numbers, I'm going to do that in the glowy math playlist. When I talk about complex numbers, I'll prove this. It's not difficult to prove. It's very straightforward algebra. But anyway, if you restrict, so the quadrants, by the way, quadrants is greater than or equal to 0. So if you restrict yourself to numbers with quadrants, quadrants is length squared. So if you restrict yourself to points with quadrants 1, i.e. the unit circle, then it forms a group. Group of real n by n matrices with determinant 1. Yeah, the special linear group, this is really important. Special linear group. It is denoted by SLN with determinant 1. I'm going to put a big star here to emphasize that this is important. SLN is the set of real n by n matrices A with determinant equal to 1. Hey, we're almost done. The defining properties 2.2.9 are often very easy to verify for a particular subgroup, and we may not carry the verification out. Okay. Every group G has two obvious subgroups, the group itself and the trivial subgroup that consists of the identity element alone. A subgroup, it's very similar to topology, how there's two trivial topologies on any space, which is every set is open and only the empty set and the whole space are open. Anyway, a subgroup is a proper subgroup if it is not one of those two. All right, that's the end of that. Thank you for watching. I'm Dr. A.J. Kumar. What do I want to work on? So I said I want to work on things that annoy me. I'm going to work on Lingua Latina and then probably work on OP-HTTPD today. We'll have to see. Thank you for listening. That's all I have to say. Have a nice night. Founder loves you. Good night.